Today, we're doing a blind test of a mysterious material. It feels grainy, it can flow, it can pile up.
Well, it's rice. Rice?
What can you do with a bowl of rice? Cook it, obviously. But what if I told you scientists are using rice to design a smart material? And the strange part is, its behavior depends on speed. Under the right conditions, the faster you compress a pack of rice grains, the weaker the whole system becomes.
Wait.
Isn't that the opposite of what we expect? We usually expect materials to be stronger and stiffer when things happen faster. But rice does the opposite. Today, we're going from a bowl of rice to a smart material that can switch its response without chips or sensors. To understand this, don't think of rice as one solid block. Rice is more like a crowd of tiny particles. Pour it into a bowl, and it flows. Pack it into a vacuumed bag, and it can support weight. Scientists call this a granular material. Sand, coffee grounds, and rice are all granular materials. You can imagine it like a crowd of people in a room. When there is plenty of space, everyone can move around. But as the room gets packed, people touch shoulders, lean on each other, and get stuck. At some point, it is no longer just separate people. The whole crowd starts behaving like one collective system. A pile of rice works in a similar way. It can support weight, not because each grain is especially strong. It is because many grains touch, rub, and lock together. And this is where speed starts to matter. If you are compressing a whole crowd of grains, the response depends not only on how hard you press, but also on how fast you press. So how did scientists test this? They did not just press down on a bowl of rice by hand. They packed grains inside a small, flexible chamber. Then they pumped the air out, squeezing the grains tightly together. At that point, the grains become jammed. Then a machine presses down from above. The key is that they did not compress it at just one speed. They compressed it slowly. Then faster. Then even faster. Then they measured how much load the jammed granular system could carry. And this next graph is the key result. You do not need to read every detail, just look at one thing. The horizontal axis shows how much the rice system is deformed. The vertical axis shows the stress it can withstand. In simple terms, the higher the curve, the more it can hold. First, look at slow compression. When compressed slowly, the rice system can maintain a higher supporting stress. Now look at fast compression. When compression gets faster, the curve drops lower. In other words, higher speed means lower load-bearing capacity. This is the most counterintuitive part of the study. For rice, the faster it is compressed, the weaker the whole system becomes. And they did not test only rice. What you are seeing here is the lineup of different granular materials they tested. Steel balls, coffee powders, sand, glass beads, and other particles too. In other words, they were not just picking rice and building a story around it, they really compared different kinds of grains side by side. And each material responded differently. Some became stronger when compressed faster, some barely changed. But rice was the most counterintuitive one. In other words, the rice system does not become stiffer at higher speed. It becomes easier to weaken when compressed faster. When we say softer, it does not mean each grain literally becomes soft. It means the whole rice grain system becomes less able to support external load. In materials science, this behavior is called rate softening. In plain English, faster compression, weaker response. Most materials still followed intuition. Rice did not. So why does rice do this? The answer is not that the rice grains are being crushed. The key is
friction.
A pile of rice can hold together because the grains grip each other. They form a network of contacts. That network is like shoulders, arms, and support points in a crowd. Under slow compression, those contacts can hold together. But under faster compression, friction between rice grains drops. The grains can slide more easily. The contact network gets disrupted. The grains that used to support each other start to rearrange. So the thing that weakens is not the individual grain, it is the cooperative relationship between grains. Once friction changes, the whole crowd of grains changes. That is the beautiful part of this study. What matters is not just the grains themselves, but the interactions between them. If the story ended here, it would already be fascinating. A bowl of rice doing something this counterintuitive is surprising. But the researchers didn't stop at, "That's weird." They asked a more powerful question. If rice changes its response with speed, can speed become a material switch? In other words, can we build something that responds one way when compressed slowly, and another way when compressed quickly? Now we're no longer just talking about rice. We're talking about a material where speed itself becomes part of the design. That is exactly what the researchers tried next. They built a special structure. You can think of it as two small columns side by side. One side is filled with rice grains, the other side is filled with silica sand. The rice side becomes weaker when compressed faster. The silica sand side responds differently to speed. Put them together, and the direction of bending can switch. Under slow compression, the structure bends toward the rice side. Under fast compression, it bends toward the silica sand side. Same structure, different loading speed, different bending direction. In other words, speed itself becomes the switch. The result is not a sensor reading speed, it is a material responding to speed by itself. This matters because it does not require complicated control. No sensors, no chips. The material itself responds differently depending on loading speed. We usually think material properties are fixed. Hard is hard. Soft is soft. But this study suggests another idea. The same material can respond one way when you press it slowly, and respond differently when you hit it fast. It is not conscious. Its physical structure has speed built into its response. That makes the material itself look almost smart. So where could this idea be useful? Imagine a soft robot hand. Most of the time, it needs enough support to hold an object steadily. But if it suddenly bumps into a person, it should not become harder. It should soften, give way, and reduce harm. Or imagine a wearable exoskeleton. During normal walking, it needs some stiffness to help the wearer move steadily. But at the moment of a fall, it should become softer and absorb the impact. Helmets, sports protection, cushioning packaging, even robot skins. Supportive in normal conditions, softer under fast loading. This study is not about whether rice can be eaten. It asks whether tiny interactions between grains can become real engineering functions. So the next time you see a bowl of rice, maybe think about one more thing. You are not just looking at food, you are looking at tiny grains that bump, rub, lock and slide. Under the right conditions, those tiny interactions can become powerful functions. That is what makes science fascinating. Sometimes the most interesting discoveries do not come from distant planets or billion-dollar machines. Sometimes they come from something common in your kitchen. More details can be found in this paper.